Hey folks, we're back with Chapter 2. So let's go ahead and get started. Well, as you've seen in the past chapter, there are ridiculous amounts of chemistry. And that's to be said for any branch of academia. If you study psychology, there are many different, not just branches of psychology, but methods of practicing psychology and psychiatry. So, hey, tons of stuff out there. But they all deal with the same exact thing. They deal with matter. Matter is defined as anything that occupies space and possesses mass. You're going to hear this numerous times. So a little bit of history here before we get full into the lecture. One, I feel that I need to apologize for typos. When I create lessons like what you see here, I actually use a speech dictation software. Now and then something kind of jumps in there and makes no sense whatsoever. If you do catch something like that and I happen to miss it, just send me a slide and say, hey, can you explain this? And that really reinforces the idea that if you bump into something you don't understand, send me an email. Send me an email. Contact me during my online office hours. Do something. Take some responsibility for your education so that you can get the clarification you need to succeed. The second thing is a book like this one. This is usually written by multiple chapter editors. There's one general author who creates the structure and framework of the entire book, but then he or she may ask to go through and do different chapters. And a book like this may have actually different authors for different chapters, which is why there may be repetition. There may be something annoying. It's like, oh my God, can you just stop saying it? Please. So just be aware of that. One type of matter can be distinguished from another because no individual substance has all of the same properties as another. So I say, well, hey, wait a second, liquids are liquids. Well, liquids are liquids, gases are gases, solids are solids. But even among the elements, there are subtle differences in regards to their chemical makeup that make them different. There are two general properties, chemical properties, physical properties. And a chemical property of a substance is a characteristic that can only be studied at the risk of changing the identity of the substance. So for instance, there's a picture of an apple here. And it's like, well, wait a second. Physical property of an apple is, yeah, it's an apple. No matter what you do to it, it's going to be an apple. But when you bite into the apple, the flesh of the apple is usually a white color, a cream color. Then a reaction takes place, an oxidation reaction, and the color changes. So even though the physical properties of the apple have changed, have remained the same, a chemical change has taken place, and it is something different than it was before slightly. Physical properties are a characteristic of a substance which can obviously be studied without changing the identity of the substance. Rules of thumb, anything we can observe with our senses, color, odor, taste, solubility, viscosity, and density, are all examples of physical properties. Burning something, watching the substance react with another, and anything else that actually changes the matter would be more than likely a chemical property. And if I'm asking you questions, I'm probably going to go along those lines. Now, there is some debate here because there are technically 4 states of matter. The fourth one not mentioned here, you see in the picture, called plasma. But the 3 states, the 3 states that we are primarily worried about are solids, liquids, and gas. A solid substance has a definite shape and a definite volume. The particles are very tightly packed, very organized, and they do not flow. Okay? Some solids may sublimate, because generally you have to go from a solid to a liquid to a gas. When you sublimate, you go right from a solid directly to the gas state without becoming a liquid. A liquid substance has definite volume, like a solid, but it does not have a definite shape. Okay? Particles of liquid are slightly further apart than those of a solid. They're able to move, but they cannot move so much they separate from each other. So if I take a liquid and I pour it, it's going to flow. If I take rock and I melt rock, we'll say for the sake of argument, because I know lava is a bit something more than just rock, but if I heat up rock enough, it will become a liquid, at which point it will flow. Has definite volume, but no definite shape. When it hardens again into a solid, it is very much a definite shape. And then gases, they assume the shape and fill any container in which they're defined. They do not by themselves have definite shape or volume. They require a container. Particles of gas are independent of each other, relatively far apart, and allow it to be flexible and fill any container it's in. If it's a square container, it becomes a square. If it's a triangle, it becomes a triangle, etc. We've seen that matter has both chemical and physical properties, and this is the same for changes in matter. There are physical changes and chemical changes. Physical change alters the physical characteristic of the matter. Cutting, tearing, grinding, changes of state are physical changes. No new substances are formed. The chemical nature of the matter undergoing the change is not altered. If we freeze water, it becomes ice. If ice melts, it becomes water. If we boil it, it becomes water vapor. Chemical change alters the chemical characteristics of matter. In the process, new substances are formed that have both different chemical and physical properties as compared to the substances from which they were formed. If we separate the water into hydrogen and oxygen, we get two separate elements. We no longer have water. We have hydrogen and we have oxygen, and without anything more done to it, it will never return to water. So now we go into categories of matter, not just states of matter, but categories. We have elements, compounds, and mixtures. Elements have the same properties throughout. They are a pure substance, cannot be broken down or decomposed by chemical means into more simple substances. Elements can also be called homogeneous. You're going to see homogeneous a lot. In embalming, in anatomy, chemistry, you name it. Elements are exactly that, elementary or basic. They're the founding blocks of matter. Water is composed of two elements, hydrogen and oxygen, in a specific ratio. We'll look at ratios later. If we separate the hydrogen and oxygen, we cannot break down hydrogen and oxygen any further. Compounds are homogeneous, pure substances composed of two or more elements chemically combined in definite proportion by weight. A compound formed by chemical combination has both chemical and physical properties which are different from the individual elements that united to produce it. Okay? If I take two items, hydrogen, oxygen, make a compound with them, it should have different chemical and physical properties than the two gases I used. Compounds obviously can then be broken back down into their elements by chemical means. Mixtures. Physical combinations of two or more substances not chemically combined. Mixtures may have their component parts in any proportion. Mixtures can generally be separated into their component by physical means, okay? So, compounds. In order to decompose, break down a compound, a chemical reaction has to take place, whereas with a mixture, I can do it without the chemical reaction. Generally, physical means are fine. Two basic forms of mixtures. Homogeneous mixtures are ones in which the individual parts are dispersed evenly throughout the mixture, so it appears the same throughout, and they usually, you can't figure out what's what. It looks completely combined. A heterogeneous mixture is one that consists of parts having different properties. It is not uniform throughout the mixture. These components can usually be detected. Matter is composed of basic substances called elements. An element can be defined as the fundamental form of matter. And as we've seen, because they're fundamental or basic, cannot break them down chemically into anything more simple. There's over 100 elements which have been identified, and about 90 of these are natural. However, when we started playing with reactors and stuff, we started creating new elements. We could now make our own. And as science progresses, we continue to make elements. Despite the vast number of elements that we have, only a relatively small number are necessary for life as we know it. Some elements occur in very, very limited quantity on Earth. Each element has been assigned an atomic symbol to represent the element. Its symbol is usually an abbreviation of its name, although some come from the original Latin. When you see AU and CU for certain compounds, they come from the original Latin names for those elements. The first letter of a symbol, of an elemental symbol, is always capitalized, and if there is a second one, it is always lowercase. Elements are generally defined into two large groups: metals versus nonmetals. Okay? Metals versus nonmetals. And I know this particular picture has metalloid in the middle of it, but we're not going to worry about metalloids. This is extremely basic chemistry we're studying here. Metals, they shine, they have luster, they reflect light. They're ductile, can be made into wire. Some are malleable. You can hammer them into thin sheets. They have a high tensile strength. They don't break very easy. They can usually conduct heat and electricity. And many are solids. But the most common liquid metal, the lone standout, is mercury, which is extremely deadly and toxic to us. But mercury at room temperature exists as a liquid. So you know bloody well someone's probably going to ask you a question on that. Nonmetals are the exact opposites. They do not have luster or shine. They do not reflect light. They're not ductile or malleable. They're usually brittle and fragile. They don't conduct heat or electricity. And while some are solids, others are liquids and gases. Metals are usually on the left side of the periodic table. Nonmetals are found on the right. Two specific nonmetal groups, which we'll study a bit more in depth, are the halogens and the noble gases. And yes, you will be responsible for all of the elements listed in the book. You should know the name, you should know probably the atomic number, and you should definitely know the abbreviation. Okay? You need to know the names and abbreviations. Most certainly. You are more than likely ever going to be asked about names and their abbreviations, probably rather than numbers. So if you're going to put a priority on something, make it names and abbreviations. A compound refers to a pure substance. It's composed of two or more elements which are chemically combined in a definite proportion by weight. Definition, note card it, memorize it, important. Compounds can be decomposed, broken down by chemical means into component elements. When a compound is formed, the constituent elements' physical and chemical characteristics are lost, replaced by the physical and chemical characteristics of the new compound. Law of definite proportion states that when elements combine to form a compound, they do so in a definite proportion or ratio with constant composition. It's also known as the law of constant compositions. Don't make this hard. Whenever hydrogen and oxygen combine to form water, it is two hydrogens, one oxygen, H2O. That is all this says. If we're going to form something, it always has to form the same exact way. The law of multiple proportions applies to situations in which the same elements combine to form more than one compound. It states when elements combine to form more than one possible compound, the ratio of the weight of one element when compared with the fixed weight of the other element can be expressed in some small whole number. If elements combine to form more than one compound, again, each compound must have a unique ratio of elements. Water, H2O. Hydrogen peroxide, H2O2. If it can form one compound, has to be in that ratio. If it can form more than one type of compound, then the ratio for that one must also be unique. Each element is made up of very small units of matter which have all the unique characteristics of the element. These are known as atoms. Atoms are the basic structural unit of an element. They are extraordinarily small, and the smallest unit of an element is an atom of that element. Okay? Some of you probably losing your minds right now. Well, scientists have discovered even smaller particles. I'm not going to worry about it. Deep breath. Okay? Deep breath. Atoms of the same element will always have the same chemical and physical properties, except for possible difference in their masses. They're going to be made up the same, but they might weigh differently, quote unquote. You're going to see where weight and mass are two different things. An atom is made up of two general areas: a nucleus and surrounding orbits, a center and things that surround the center. The nucleus is the central core of the atom. The orbits are the particles that orbit or surround the nucleus, not unlike the moon, which orbits our Earth. There are three fundamental particles in an atom. These are obviously important: protons, neutrons. These are in the nucleus. Electrons in the orbit or the shell. A proton has a mass or weight. Remember, they're usually used interchangeably here on Earth because of gravity. Mass or weight of approximately 1 atomic mass unit, 1 AMU, and a charge of positive 1 plus 1. Proton, 1 plus 1. A neutron has a mass or weight of approximately 1 atomic mass unit, 1 AMU, and no charge. It's neutral. An electron, he's been working out. He's got a mass or weight of 1/1837th of an atomic mass unit. So we consider its weight as negligible or 0. Electrons have charge of -1. Protons +1. Electrons -1. Neutrons neutral. No charge, 0 charge. Modern chemistry, atomic theory discusses components of even these items, as I've alluded to earlier, but we're not going to do that because that's just absolutely insane if people start requiring funeral directors to be worried about quarks and garbage like that. The atomic number or element of the given element represents the number of protons found in the nucleus of the atom of that element. So if you see a number that says 6, that means it has 6 protons. Because each atom starts out electrically neutral, there has to be an equal number of protons and electrons. The atomic number, therefore, not only represents the number of protons, but also the standard number of electrons in orbits. Again, don't make this hard. If the number says 6, you have to have a net charge of 0 in an element. So that means 6 protons and 6 electrons. Atomic weight is a relative weight of the atom as compared to another element. And carbon-12 is the standard element chosen by chemists for comparison. If an element weighs 3 times the weight of this element, it has a relative weight of 36. Since, just going to say, carbon-12 probably weighs 12. The mass number of the element is also its weight. It's based specifically on the number of particles in the nucleus that possess weight. Now, if you go back a couple of slides, remember that, hey, protons, that's the easy one. Weighs 1 plus 1. Neutrons weigh 1 but have no charge. So if an element has 4 protons, 3 neutrons, it's going to have an atomic mass equal to 7. And this is how this concept is derived. Electrons are not counted towards the weight. Worry about protons and neutrons. And if you have an atomic number and you have an atomic total weight, deduct the number of protons, and bada bing, you have neutrons. Well, it's nearly impossible to weigh one single atom of an element. That doesn't mean people don't try because, even scientists have the, dude, hold my beer moment. It is much easier to weigh them as a group. And chemists have chosen the number of atoms to weigh so that we can compare to a number of atoms. And this is called a mole, okay? Mole refers to a very large number of atoms. It's a ridiculous number, okay? It's called Avogadro's number. I'm not even going to get into the 6.023 times 10 to the 23rd power. What the shizzle? A quantity equivalent to 1 mole of a substance has a weight in grams equal to its atomic weight. It is because of this that we can go directly from the mass or weight given in the periodic table of elements to grams without conversion of the units. Again, if you're not getting that, it's really, really simple. When they built the scale, they built it with this concept in mind that if it says grams, that's how many atoms have to be in the nucleus. Automatic there. The definition of atomic weight should still be considered to be the sum weights of all the subatomic particles. Electrons, protons, and neutrons. Because remember, electrons weigh basically 0. So when we give an atomic weight, we only consider the protons and neutrons, but under the larger umbrella in theory, it's all of it together. And we often approximate the atomic weight by simply using the mass number of the element, which considers only those things, only those particles with significant weights. Some elements are known to have atoms with different weights or masses, and this is because they have different numbers of neutrons. Remember, the element has to equal 0 between positive and negative protons and electrons. Element has to equal 0. So the only thing that we can change is the stuff that has no charge, which are the neutrons, and these are known as isotopes. Isotopes are atoms of the same element, but they have different atomic weights or different numbers of neutrons. So I throw carbon at you right here. Carbon, 6 protons, 6 neutrons. Well, carbon 12. Carbon 13, we add a neutron. Carbon 14, we add another neutron. Everything else stays the same. It is always possible to compute the number of neutrons in a given atom by subtracting the atomic number from the atomic weight or mass. I've already beat this one down. Take the total number of protons. It's going to be right there. Carbon, little 6 above it. And then it says the total weight of this element is 13. How many neutrons are there? Well, you're going to have to go through this really heavy mathematical computation of subtracting 6 from 13. Hydrogen is no different. You can see the isotopes of hydrogen. You say, well, how can we see P and N's here? Hey, proton, neutron, neutron. Gives you the formula. Okay, gives you the formula. Gives you a little summary. So how are these electrons arranged? This specific order. They're always arranged in this order, and these are referred to as energy levels. And this little diagram here is going to help you out. Nucleus, protons, and neutrons, no electrons, no one cares. First energy level outside can hold a maximum of 2 electrons. Second, can hold a maximum of 8, etc., etc. Notice it says, new word, orbitals. We'll get there. You cannot bump up an energy level until you have filled the previous. You can't just randomly throw electrons at an orbit and they're going to stick. They have to fill. They have to fill before you go into the next levels. And this is called electronic configuration. Electrons always fill the orbits from left to right. The coefficients, large number before the small letter, represent the shell number and a shell number or quantum number. No, really, I can read English. At least I pretend I can. So right now, some people are probably losing their minds. What the shizzle is going on here? Well, remember, go back to the picture. Okay, 1, 2, 3. 1, 1, 1, 2. So by this point, we know that the ones are filled. Now, remember what it said here. If you look down here, second energy level can hold a maximum of 8 electrons distributed over 4 orbitals. Now, I know orbitals are coming up. So there's going to be 4 different little things going on here that we have to fill until we total up 8 electrons. And once we hit 8 electrons, we will go to the next full orbit and then go into the smaller orbitals. And this kind of tells you where things are. The largest of the coefficients in the electronic configuration always represent the outermost shell of the atom. Okay? The outermost shell is always the period or row of the number of the element in the periodic table. Well, look at what's going on here. Rows go this way. Well, if it's here, 1, 2, 3. Notice the trend? Okay. Maximum number of electrons in a given shell may be represented by the formula 2n squared, where n is the quantum number. Orbits, the smaller letters, represent the different energy levels within a given shell. The lowest energy level in any shell is always the s orbit. Okay, always the s orbit. And orbits are said to be made up of orbitals, each of which contain 2 electrons with opposite spins. Each orbit has the following numbers of orbitals and possible electrons. So s orbit, 1 orbital, 2 electrons. Let's jump back here. S orbit, right there. Okay? Then if we go to the next one, we have S's and P's. And things start building up. Use this little electronic configuration thing here to kind of help you out with that. Okay? It looks so complicated. Oh my God, look at all the numbers, blah. Okay? But it's really not. It's really, really not. Remember, it said 2 on the first orbit, 8 on the next. So it tells you 2 on S1 level, total of 8 here, etc., etc., etc. Those numbers all add up. There are ways to do this. Okay, there are ways to do this, and it tells you how to do this little diagonal thing here. I'm not going to spend a lot of time on this. Okay, I'm not going to ask you a lot of questions. I'm more apt just to ask you, based on this atomic weight, how many are going to be in an orbit, rather than have you go crazy. I'm more apt to ask you, hey, how many orbitals are there in a p orbit? Okay, if I have an element that has s, p, and d, what are the total number of electrons that I can possibly have? What is the total number of orbitals with 3 orbits of s, p, and d, et cetera, et cetera, et cetera? So I give you more pictures about, how these things kind of interact in ways so you can kind of comprehend what the book is saying. Again, I'm not gonna beat you to death on this. I'm going to ask you very finite black and white questions. So valence electrons. Valence electrons are those electrons found in the outermost shell, the largest of the coefficients in the electronic configuration. The outermost shell can contain no more than 8 electrons at any given time. Okay, so we're looking for the outermost shell. This guy right here. 1, 2, 3, 4, 5, 6, 7. Whoops. Computer got in the way. 8. I have 8 right there. That's it. It says these electrons are responsible for not only the chemical properties, but many of its physical properties as well. This can influence how well it reacts with other things, etc. So it's been talking about the periodic table. Well, the periodic table of the elements is a horizontal and vertical arrangement of the elements in order of their increasing atomic numbers. The elements are arranged in horizontal rows called periods, and they represent the outermost shell of electrons for that particular element. Remember that the coefficients in the electronic configuration always represent the shell numbers. So the largest coefficient is the outermost shell. The elements are also grouped together vertically according to their similar chemical properties. This group number will represent the number of valence electrons. The only exception is helium. So you're more apt to be asked about helium because it's an exception, which has only 2 valence electrons, but is still an inert or noble gas found in group 8 of the periodic table. Certain groups or families have special names which you should know. So if we go over here and we compare this periodic table to that one, you can see our boy helium, but everyone else over here has valence electrons of 8. But because helium is a noble gas, they stuff him over there because he's special. So looking at this, folks, these are the elements you're responsible for. You're responsible for knowing, again, the names of what the elements are, the abbreviations of them, and the atomic number. Okay? I'm not going to go crazy with like atomic weights and stuff like that. I may ask you to compute atomic weight, but I will almost universally give you the atomic number, unless it's like one of the huge ones like carbon or something like that. You should know, carbon has 6 protons. Carbon is huge. So folks, thank you for your attention. We will see you next time.